We'll go to our second presentation from University of Washington. Dr. Don Lehman will present on economic pier-to-pile connections for permanently cased shaft pipes. Dr. Lehman?
Today I'm going to talk about some of the research results that we have on a direct connection, similar to what Mark talked about, but instead of a cast in place shaft, we have a case shaft. So this is similar to some of the research that we've been doing previously in collaboration with FIU. So this is work that Charles Roeder and I have been doing with our students and some visiting scholars from China. And we have looked at using concrete filled steel tubes as different elements in a bridge. And in this case, we're looking at a concrete filled tube used as a pile. And a lot of times those are called drilled shafts or case shafts, depending on the construction type and depending on the soil conditions. But the idea here is to look at a direct connection between the reinforced concrete pier and the pile. And this is a photograph showing a situation like this in a WashDOT bridge, where the image on the left, this sketch is showing a cast in place reinforced concrete pier going into a reinforced concrete shaft connection. You can see them placing the tube on the right, and the purple lines are showing the case portion of that shaft. So you can see that these are already being used, and there are these questions of how do you transfer the force from the pier into the pile, especially what length does the reinforcement need to be? Could we put in some supplemental mechanical reinforcement to be able to improve the bond condition? So that's what we're looking at. So we've been doing this right now through an analytical study. So the objectives are presented here. Obviously, we want this to develop a new connection, which is analytically and experimentally validated, ending up with design expressions. So what I'm going to talk about today is a study parameter that we have done with a pretty advanced finite element analysis. And from that study parameter, we have some initial design recommendations. And we use this really to develop an experimental test matrix. And so the next phase of the research will be to conduct 4 half-scale connection tests. So the first thing I want to talk about is the finite element model. There are a lot of details to this model, and I'm not going to go into it because there just isn't enough time, but just to show you what we're thinking of. So because we're really using this in part to understand what we need to test in the lab, which is shown on the left here, we're modeling the lab specimen in LS-DYNA. So we're modeling the components of the lab specimen, so the reinforced concrete column, which is shown on the top. And the reinforced concrete column, in general, we were using a diameter of about 24 inches. And then we're modeling the steel tube of the shaft. And in general, that tube is between 24 and up to 40 inches, which we'll talk about a little bit later. And then there's a transfer beam. That transfer beam is used to transfer the force into the block, which is shown here on the left in terms of the setup for the testing that will be conducted. And our student is collaborating with Professor Eberhardt, Professor Stanton's student, because you can see that the test setup is quite similar. So an overview of the finite element model, there are a lot of different components. So the first component is, how do you model the concrete and reinforced concrete pier? So we're using a CDPM, which is a concrete damage plasticity model in LS-DYNA. That concrete damage plasticity model has a lot of different parameters that control it. The most important parameters are what the energy is in terms of the compressive damage. So that's the EFC parameter, as well as the tension damage. But what I'll show you when I show you the results is really this, what I'm going to call a compression damage parameter, this EFC parameter. So we looked at what is the right value for that in terms of the cover and the core concrete of the reinforced concrete pier. Of course, we need to be able to model the transverse and the longitudinal reinforcement. We're using beam elements for this. That's so that we can look at the axial stresses in those elements, as well as be able to model bar buckling. And then, of course, we need a model to to model the slip or the transfer, shear transfer between the reinforcing bar and the concrete. So this is based on some work that was done by Marcia DeLusso, and so we'll use that data to be able to develop our slip model. And then we use some different test data. This is some data that was done, a test that was conducted by Lowe and Maley to validate the model. And so we get pretty good results. They're not perfect, but they're pretty good. We also did some more recent tests on Bayrak that Bayrak did at UT Austin. And then we also need to model the concrete filled tube. So the question now is, what do we need to do for the concrete core and the steel tube? So again, we go in and use the concrete damage plasticity model for the concrete core. And then we also need an interface model between the tube and the concrete. So we have a model that we developed using the cohesive model in LS Dyna for that, and validated that with some prior tests that we had done on straight seam tubes and spiral well tubes. If you look at these plots that I'm showing on the right, you can see that there's quite a big difference between the scales. That's because a straight seam tube has much less bond capacity than a spiral well tube. Now, it's much more typical in a shaft to use a straight seam tube because the tube diameter is so large, and the spiral well tube is usually not available in those diameters. So the work that we're doing here is looking at using the bond model for the straight seam tube. And then we validated that using some work that was done by Han. In this case, Han was connecting a concrete filled tube into a reinforced concrete shaft. You can see that in the photograph on the right, but that was the closest connection that we had found. So we wanted to simulate that, and you can see that we did a pretty good job of simulating that. We did more than verify it in terms of just the hysteretic response. We looked at damage as well, but this here just gives you an idea of the work that we've done on the model verification. So what we did then is we took this model and we did a pretty extensive parametric study. So like I said in the beginning, we're really looking at this transfer mechanism between the reinforced concrete pier and the reinforced shaft, which is shown here on the right. And so I'm showing in red a tension force in the bar, essentially, and then in gray a compression force in the bar and the concrete. And those forces, as well as the shear force, need to be transferred down into the concrete filled tube. So in order to do that, we need to, of course, be able to sustain the strutting action of the concrete. And we have looked at two different ways to do this. So one is embed the reinforcing steel deep enough so that we have adequate anchorage without any supplemental mechanical anchorage. Or the second thing to do is add a supplemental steel rib, which I'll just refer to usually as a rib here, which you can see in the figure on the right, shown as a little grade in square. And so we looked at what dimensions that rib should have, where it should be located relative to the top of the tube. We also looked at different reinforcing bar sizes. We looked at different steel tube diameters. We looked at the embedment depth as a function of D. So this is a lot of different parameters. I'm not going to show them all to you just because of time. If there's interest, I'm happy to talk about them with you later. So in order to evaluate them, we looked at 4 different aspects of the response. We looked at the overall force displacement response, we looked at degradation and strength, energy dissipation, and concrete damage. And so I'm going to just go through some of this quickly. So the first thing that we looked at, like I said, was what size should the rib be? And these are from a publication that we've just put together, so everything is in metric, but I'll talk about them in standard units. So if you see here, we looked at 3 different ribs. So the figure on the left shows what happens if you don't have a rib and you embed the reinforcement to the ASTO length, development length. The figure in the middle shows what if you have a rib that's an inch by an inch, and the figure on the right shows what happens if you have a rib that's 2 inches by 2 inches. And the thing you can see here is that when you have the rib that's 2 inches by 2 inches, you really have a lot less strength degradation. And that's shown in the bottom figure on the left. So that shows what's the percentage of strength degradation at a displacement ductility of 6. And you can see that we get the least amount of strength degradation with a rib that's 2 inches by 2 inches. the figure on the right is showing an equivalent damping ratio, which is really just a way to look at energy dissipation. And you can see there that we have the most energy dissipation for the 2-inch rib. So we decided to use that. And then we started looking at different embedment depths without the rib for different tube diameters. So we looked at 2 different tube diameters. And the thing here to see just from the force displacement response is that if you look at the figures on the bottom where we embed the reinforcement 1D or 1.5D, we're really not seeing a big difference. So from that, we're basically saying that your embedment depth needs to be at least 1 times the tube diameter if you're not using a rib. Then another important aspect of the response, and this I'll have the most figures on, is the location of the rib. So the location of the rib could be, it could be 2 inches down, it could be 6 inches down, it could be 14 inches down, which is, so the figure on the upper left shows what happens if you don't have a rib at all. And you can see that with the number 9 bar, which is shown in blue, we get a lot more strength degradation. If we put in a rib 2 inches or 6 inches down, then we get, I'm getting a lot of feedback, I'm not sure why, but and if you can see there's not a huge amount of difference. If we put it pretty deep into the tube, we are not getting very good anchorage. And we can look at that more significantly here, where this is showing how much strength degradation we get. We get more strength degradation if we have a number 9 bar. You can see that with both the number 9 and the number 7 bar, the minimum amount of strength degradation is between 2 inches and 6 inches. That's also maximizing the energy dissipation. And this is showing you how much damage there is in the concrete. So the figure on the left shows,
excuse me.
Yeah.
Can you wrap up in a minute?
Yes. So this is basically just showing you, if you look at the figures here, from 2 inches to 6 inches to 18 inches, the more red there is, the more concrete damage there is, especially when you start looking at the tube. And so our recommendation there is that if you embed the reinforcement, it needs to be at least, of course, the AASHTO embedment depth. If you use a supplemental rib, it should be 2 inches square, and it should be placed 2 to 6 inches below the top of the tube. And if you're not using a supplemental rib, you need to embed the reinforcement the larger of the AASHTO embedment depth and 1 times the diameter of the tube. And the next phase, as I said before, will be 4 tests. And we're starting out looking at tests where we've just embedding the reinforcement, the AASHTO development length, so that we can understand kind of what happens with that specimen and then what the impact of the rib will be. So thank you very much for your time and attention. I'm happy to answer questions if there's time.
Thank you very much, Dr. Lehman. It was a great presentation. Unfortunately, we don't have time. We have to switch to next presentation. I appreciate you. Thank you.